Hey everybody, so in this video, I will be talking about some of the basic considerations you would have to make in designing a wind tunnel experiment, and then show you how our setup looks like for testing the airfoils in your project. So one of the first things you need to think about before designing a wind tunnel experiment is to figure out the Reynolds number that you need to test at. And remember, Reynolds number is defined as the fluid density multiplied by the free stream velocity multiplied by the characteristic length, all divided by the dynamic viscosity. There are a few other ways to write this, but let's just stick with this one for simplicity. And to save you some confusion, characteristic length is defined differently for different objects. For an airfoil, which is what we're interested in, the characteristic length is just the chord length. So that's the definition of the Reynolds number, and you're probably taught that physically, this represents the ratio between the inertial force and the viscous force. But I always thought that this wasn't that easy to understand intuitively, so I'm going to spend a minute here to illustrate how I understand Reynolds number. Imagine a simple flow through a pipe, where this guy here represents one fluid particle. We expect the particle to move down the pipe in a straight line like this. But in reality, nothing is so orderly like that, and instead, this slightly shaky path would be a more accurate depiction of the flow. And those random little bumps are called perturbations, which can happen to anything with real mass and real velocity, and hence related to the inertial force of the fluid flow. When there is enough viscous force, which I imagine as fluid particles holding hands with each other, it basically dampens whatever small perturbations there are, hence looking like a laminar flow. Blood flow in the vein is a good example of a laminar pipe flow where the viscous forces dominate. But when the inertial force gets a little too strong, some of the particles start losing grip of each other, and your flow doesn't look as laminar as before. Until finally, when there's just too much momentum, they just can't hold on to each other, and this would be your full-on turbulent flow. So I hope this helps you understand Reynolds number a bit more intuitively, but I gotta admit, this way of looking at Reynolds number can be a bit misleading, because even if the bulk of the flow is very turbulent, right, you would still expect boundary layers near the walls of an object, which is very much dominated by viscous forces. So just keep in mind that Reynolds number is a very macroscopic kind of way of characterizing the flow, and that locally you could have either laminar or turbulent flows. The key thing to understand here is that Reynolds number provides a way of scaling an experiment to a lab size, where oftentimes it's difficult to fit a one-to-one full-scale model. So let's say we were interested in the aerodynamic flow of this car, driving at 15 meters per second or about 50 kilometers per hour. You would expect to get some sort of drag force and some kind of boundary layer. Well, what the Reynolds number tells us is that if you want the same kind of dynamics in a model that is 3 times smaller in geometry, you would need to increase the speed by 3 times, giving the scaled down model the same Reynolds number as the original. Okay, so that sounds pretty straightforward, but I lied a little just now. Matching the Reynolds number is only the viscous portion of scaling fluid flows. We've completely ignored compressibility so far, and so to really scale the flow accurately, we need to match the Mach number as well. But like most things in life, you have to make a compromise. You can't have both. They're both dependent on velocity. So the general rule is that you match the Reynolds number for low speed stuff, but when compressibility comes into play, you match the Mach number. Now, you might be sitting there being all clever and tell me, well, can I also play around with the fluid density and viscosity to match the similarities? And the answer to that is sure, and there is something called water tunnels. But as you can imagine, there will be a whole nother set of engineering considerations to build such a facility. Another thing to consider is something called blockage ratio. Let's say this is the cross-section of a wind tunnel. With nothing inside, the airflow is pretty uniform. Now, if you were to put a car in the middle of the tunnel, all that flow that's being blocked need to get through one way or another because of conservation of mass. So, for the example of this car, you end up with a different airflow than what you would get on the open road because the physical existence of the walls in the tunnel affect the flow. So, to mitigate this problem, a blockage ratio of less than 10% is the common practice. Now I'll show you how our test setup looks like. Here we have everything we need for the rig assembly, where we're going to attach this 3D printed airfoil, and this is the same one as figure 2 in your project handout. So we have the upper surface here and the lower surface here. These two holes are where we attach it to the rig, and they're actually these steel threaded inserts, which I just kind of embedded into the airfoil. Okay, so if we mount this airfoil, the air will be coming in like this, which causes lifting force and drag force. We're going to capture those forces using this load cell right here. But it's expensive, so I'm being careful here. And if you look closer at the load cell, there's a reference axis inscribed. Basically, we're going to fix the top side of the load cell and mount the airfoil on the bottom, like this. And the forces acting on the airfoil will push these two halves of the load cell, creating voltage signals that we read as forces and moments. But in order for me to attach the airfoil, I first need to attach this plate here to the bottom half of the load cell, using these 3 bolts here. I'm just making sure the alignment is correct, and let's secure it. So this plate is now like an extension to the bottom half of the load cell. And now I'm going to attach a second layer to it. So that I can mount this acrylic disc that helps us rotate the airfoil. But before I do that, I need to bolt the airfoil onto the acrylic disc first, using the 2 threaded inserts that I embedded earlier. Let's put a couple of washers. And secured. Now let's put these two things together. Okay, so now I need to pass this cable through here, which was pretty tedious if you ask me. And I'm going to attach this to the top side of the load cell using 3 bolts. Okay, so this whole assembly can rotate around this ring that I'm holding. Now this outer ring needs to be completely fixed to this steel sheet piece right here. So let's get our cable through first. Get a couple of washers and bolts. And secured. Okay, so the airfoil can rotate about this steel sheet piece. Okay, so now let's put the whole thing that we just made into the tunnel. And you see how the acrylic disc covers the hole perfectly? Here's a closer look from above. Okay, now we need to secure our assembly onto these rails. But before I tighten the bolts, I need to make sure that the acrylic disc isn't actually touching the hole. And that's because if it's touching, some of the forces from the airfoil will be transferred away from the load cell and into the structure. So I just kind of shimmy this piece of paper around the gap, and if it's all good, I secure the bolts. Now the airfoil can still rotate pretty easily. And I'm going to set it to 0 degrees. And if you see here, the angles are marked here. And then I just put these 2 bolts through to clamp the rotating disc. Alright, that's the assembly, and now we're ready to start running the wind tunnel, which I will show you in the next video.